All right. Okay. So we're not recording. Is it okay to start, Amnon?
Yes, sure.
Okay. So it's a great pleasure to have Amnon Neeman with us today from ANU, Australian National University. He is going to talk about uniqueness theorems for DG enhancements.
Thank you very much. It's a pleasure to be talking to Zag. So I'll begin with explaining what the terminology means. I'll try to be fast. Then I'll go through a history of the results. And finally, I will mention the new ones. So I'll try to do the first parts relatively quickly. It's meant to mostly be a reminder. So for us, K will be a commutative ring, not necessarily a field. And the categories we care about are the category K mod of all K modules, and the category C of K of all cochain complexes of K modules. Now, C of K, the objects of C of K are the cochain complexes, and the morphisms are the cochain maps, the honest cochain maps. So commutative diagrams as below. Now, both of these are closed monoidal categories. They have a tensor product and an internal Hom. This is because the ring is commutative, the ring K is commutative, the tensor product of two K modules is again a K module, and Hom AB is a K module. And for the cochain complexes, the formula for the tensor product and the Hom complex is the usual one. And both have identities for the tensor product. So the identity for the tensor product of of two cochain complexes is the complex with K in degree 0 and 0 everywhere else. Okay, so now one can define what one means by a K linear category and by a DG category. So the short definition is that a K linear category is a category enriched over K mod, and a DG category is a category enriched over C of K. Anytime you have a closed monoidal category, you can enrich another category over it. And if you've read Kelly's 1982 book, you will know all about enriched categories, but let me quickly remind you what this means in concrete terms. So to give a C, the structure of a DG category, means, first of all, it must have objects. So given, you have to have a set of objects, ob C. Now, our categories will be small in this talk, small in some universe of our choice. And so you have a set of objects, and then you have to have the morphisms. So given any two objects, you give a cochain complex of morphisms. Hom C1, C2 is a cochain complex, not a set. And there has to be a composition law. So given the cochain complex Hom C2, C1, C2, and the cochain complex Hom C2, C3, composition is a map from the tensor product of cochain complexes to the cochain complex Hom C1, C3, meaning a cochain map. And then you also have to have an identity. So for every object C, there must be a map from the identity of the tensor product to Hom CC. And these must satisfy the obvious properties. So associativity and the identity acts as identity. And now the next concept is that of a DG functor. So a DG functor is a functor respecting all the structure. So it has to give a function on objects. It takes objects of C to objects of D. Given any two objects of C, there has to be a cochain map from the cochain complex hom C dash to the cochain complex hom F of C dashed, and composition and identities are respected. So this defines for us what a DG category and a DG functor is. And given a DG category, you can always form the category H naught of C. So the objects are the same, but hom in H naught of C from C1 to C2 is H naught of the cochain complex hom C1, C2. So whereas in the DG category, hom C1, C2 is a cochain complex, in the category H naught of C, it's just a K module. And composition is what you usually think of as composition. And a DG functor induces a K-linear functor between K-linear categories. Now, a DG category always has a Yoneda functor. Well, I mean, any category has a Yoneda functor, but an enriched category has an enriched Yoneda functor. And because this is enriched, it lands in a DG category, and you can form mapping cones in the category of modules. In the category of functors from C up to CK, you can form mapping cones, and the category is called pre-triangulated if the essential image of the Yoneda functor is closed under mapping cones. And what's relevant to us is that anytime you have a pre-triangulated DG category, H naught of C is a K-linear triangulated category. And if F is a DG functor between pre-triangulated category, then H naught of F is a K-linear exact functor between K-linear triangulated categories. And now, if you have two DG categories, C and D, a DG functor F from C to D is called a quasi-equivalence if H naught of F is an equivalence of categories. And now we come to the first important definition. What does it mean to say that a triangulated category has a unique enhancement? It means that if you're given two DG categories, D and D dashed, with H naught of D and H naught of D dashed, both being equivalent to T as triangulated categories, then there has to be a zigzag of DG functors, all quasi-equivalences, connecting them. So a finite zigzag, which actually shows that they're equivalent, already in the category of DG categories. And what does it mean for a functor to be enhanceable? So if you have two pre-triangulated DG categories and a functor between them, so a functor from H naught of D to H naught of D dashed, you say that it's enhanceable if there's a zigzag of DG functors as shown but with all the maps going back, all the maps in the wrong direction are quasi-equivalences, invertible after taking H naught. And after taking H naught, the composite, in the obvious sense, you go back by the inverse of the maps going the wrong way, is F. So that is what it means for a functor to be enhanceable. And with these definitions, the question becomes, well, the obvious questions are, does every K-linear triangulated category have a DG enhancement? So this is question one. Can a K-linear triangulated category have two or more enhancements? And does every K-linear triangulated functor from H naught of C to H naught of D have an enhancement to C and D? So these seem natural questions, and they're old questions. So now, as I said, the first part of the talk was to state everything. So the statements are all precise. Are there any questions about the statements before I move on? The next is going to give a quick history. Okay, so the next, I go to a history. So the definition, the string of definitions I've given is all from the 1990 paper by Bondal and Kapranov. So I should say that the theory of enhancements is older. It goes back to Quillen in the 1960s and a later variant by Waldhausen. And of course, there are modern variants. There's the infinity categories, which are very popular nowadays. The advantage of the formalism of Bondal and Kapranov is that it's simple and very elegant. In fact, I've given you a complete treatment in just a few minutes, whereas I couldn't do that with the infinity category version. At least not if I couldn't give a complete and honest treatment. Anyway, so we will be doing things in the DG context, and the paper which started this is from 1990. And the first answer, so the first counterexample, so showing that there exists a non-enhanceable exact functor of triangulated categories, appeared 2 years later. It's a result of mine. And well, I wasn't aware of the Bondal and Kapranov paper, partly because I don't read Russian. I mean, this was published in Russia in 1990, and the English translation was not until 1991. Anyway, I wasn't aware of it. So my paper is in an older language, but also it's topological. So it's a functor from an algebraic category to a topological one, but it's still, it is in the older language a non-enhanceable functor. And again, everyone, so already in the, so we are still in the, I'm proceeding chronologically, and we're still in the early 90s. And in the early 90s, people suspected that there will be triangulated categories with two enhancements, but no one knew how to prove such a result. So here is the suspected counterexample. So you can look at the following really dumb category. So the category consists, you take K to be Z mod P, and you declare that the shift functor iterated 2 times P to the N minus 2 times is the identity. And this is going to be a triangulated category with a tensor product. And every object is a direct sum of shifts of the unit of the tensor. And the unit of the tensor satisfies the rules that hom from 1 to a shift of 1 is either 0 or k. So it's either 0 or one-dimensional. And the rule is that one. And the exact triangles are all the stupid exact triangles. There are no interesting ones. So there are 2 enrichments. So the first is, you can think of it as the category of graded vector spaces over the graded field, K of x inverse. But you can also think of it as the category of modules of the nth Morava K theory. And this gives 2 infinity category structures on this, if you want to use modern language. And already in the mid-90s, everyone expected these to be inequivalent, but no one knew how to prove it. So this is how things stood in the mid-90s. And slightly later, in 1995, you have this amazing theorem of Olof, which says, I mean, until now, all that was known are, you'd expect everything to be false. There's an example of a functor which isn't enhanceable. There's an example of 2 categories which probably have different enhancements. But here's Olaf's theorem, which tells you that anytime you have an equivalence of the bounded-derived category of coherent sheaves on X and the bounded-derived category of coherent sheaves on Y, it must be induced by a Fourier-Mukai functor, by a Fourier-Mukai kernel. It must be enhanceable. In fact, it's a theorem of Toen that a functor from bounded-derived category of coherent sheaves on X to another is enhanceable if and only if it is a Fourier-Mukai functor. So it tells you that all equivalences of bounded-derived categories of coherent sheaves are enhanceable. So you have all of these negative results I told you about, and then this, in the late 1990s, a result which seems to go the other way. Now, I'm going to stop being chronological and just say what is known about Fourier-Mukai functors. So Olaf's theorem led to a great deal of development, and let me just mention a few of the results. So Olaf's theorem was about smooth projective varieties over field K. Kawamata generalized it to stacks in the early 2000s. Kanonako and Stellari in 2007 gave a generalization which didn't assume that it was an equivalence. So under certain conditions on the functor, it has to be enhanceable. And Rizzardo generalized even more. She weakened the condition on the functor. So there is a relatively general class of functors from dB coherent on X to dB coherent on Y, which must be Fourier-Mukai. So the question becomes, are they all Fourier-Mukai? And the answer turns out to be no. So this was answered very recently. There's a counterexample due to Rizzardo and Vandenberg, which appeared in 2019. And there's a counterexample due to Vologodsky, which also appeared in 2019. The Rizzardo and Vandenberg one is better in the sense that it's linear over a field, whereas Vologodsky is linear over the dual numbers. It's linear over, no, sorry, not the dual numbers. It's linear over, well, okay. One way to say it is the length 2 Witt vectors over a field of characteristic P. Anyway, so this is what is now known about enhanceability of functors. How about uniqueness of enhancements? I told you that already in the mid-90s, it was suspected that there should be triangulated categories with more than one enhancement. But the first proof, the first honest counterexample with a proof is due to Schlichting. So in 2002, he published an example. And note how simple the example is. If you take any perfect field of characteristic P greater than 0, then you can look at the singularity category of the dual numbers. Okay, I remind you, the singularity category is the bounded-derived category of coherent sheaves divided by the bounded-derived category of vector bundles. And you can do this for the dual numbers over the field. You can do it for the length 2 Witt vectors over the field. And the two singularity categories are equivalent K-linear triangulated categories. They come with two enhancements, two natural enhancements. And Schlichting proved that these enhancements aren't equivalent if K is Z mod P. They're probably never equivalent, but Schlichting's proof works when K is a prime field. So, in the light of all of this, the next paper looks very brave. So in this paper by Bondal, Larsen, and Lunds in 2004, they conjecture that under reasonable categories have unique enhancements and exact functors between them are all enhanceable. So, I mean, in view of all the counterexamples we've seen, this is a remarkable conjecture. I mean, look at the previous slide. I mean, surely the singularity category is not a complicated category. And it has, I mean, even for a very small singularity category, it has two different enhancements. So why would you expect conjecture A to be true? I mean, conjecture B in 2000, so my guess is that Bondal, Larsen, and Lunds were not aware of Schlichting's paper. Conjecture B is more reasonable given what was known at the time. I mean, this is 2004. So at the time, Olof's theorem was known, and maybe Kawamata's theorem. So it was, I mean, the theorems that were known said that the functors were all Fourier Mukai. The counterexamples came later. Anyway, so in some sense, we have discussed B. So B is false in the generality in which Bondal, Larsen, and Lund stated it, but there are many special functors for which it is true. There are functors that have to be enhanceable. For example, equivalences, but not only equivalences. There are classes of functors which must be Fourier-Mukai. So the rest of the question will focus on question A. The rest of the talk will focus on question A. But before I focus on question A, I should say something about the categories which have no enhancement. So the question is, are there completely unreasonable categories without enhancement? And the answer is yes. So the first example of a triangulated category which has no enhancement is due to Muro, Schwede, and Strickland. And the category could hardly be simpler. It's the category of free modules over the ring Z mod 4. What could be simpler? I mean, if you want, you can take finitely generated free modules over the ring Z mod 4. So the triangulated category structure is given by the suspension. The shift functor is the identity. And the exact triangles are all isomorphs of direct sums of rotations of two really simple exact triangles. The trivial one, which is built up of an isomorphism from Z mod 4 to Z mod 4. And then the triangle which consists of 3 multiplications by 2. So of course, the category couldn't be simpler. It needs to be proved that it's triangulated, and it also needs to be proved that it doesn't have an enhancement. But those facts are true. Now, just last year, this was generalized a lot. So this paper by Rizzardo and Vandenberg show that there exist non-enhanceable categories linear over any field K. In particular, it's not a characteristic 2 phenomenon. You can get it in characteristic 0 as well. Okay, so there are pathological categories without any enhancement. So the question now becomes, what about conjecture A? So conjecture A, I mean, maybe I should go back to the conjecture. So conjecture A says that reasonable categories should have unique enhancements. And of course, this begs the question of what does reasonable mean? But this conjecture turns out to be true, and I will now give the results. So it was a brave conjecture at the time. The first positive result appeared in 2010. It's a paper by Lunds and Olof. And it proves what it says it does. It proves the uniqueness of enhancements for certain triangulated categories. Now, paper 2 is a survey. But the other 2 papers, the one by Canonaco and Stellari, improves, I mean, it's a generalization of the paper by Lunds and Olof, and it appeared in 2018. And then, so it proves better results. And okay, so for the experts, the paper by Lunds and Olof uses the techniques of compactly generated triangulated categories. The paper by Canonacco and Stellari improves the results by using the techniques of well-generated triangulated categories, whatever they are. So you can prove nice theorems using compact generation. You can prove stronger theorems using well-generated triangulated categories. And then the paper by Antio was somehow a jump. He proved much better results. And he proved it using the infinity category techniques. So it's really a jump. It proves results much stronger than the two earlier papers by infinity category techniques. And the results I want to tell you about today are from a joint paper by Canonacco, Stellari, and myself, which improve on Antio's results. I mean, they essentially solve all the open questions in Antio's paper, but they do it by going in a completely orthogonal direction. So they don't use compact generation, well generation, or infinity categories. Okay, so let me state the theorems. Okay. The way I will go about it is I will state the new theorem, the theorem by Canonacco, myself, and Stellari. Then I will tell you what was known before, and then I will tell you something about the proof. So the first theorem says that if A is any abelian category, then the derived category of A has a unique enhancement, where the derived category could come with any boundedness hypothesis. So it's either the bounded above, the bounded below, or the unbounded derived category. All four of them have unique enhancements. Okay, so now what was known before? Luntz and Olof proved that if A is a Grothendieck category with a small set of compact generators, then the unbounded derived category, D of A, has a unique enhancement. Canonacco and Stellari improved it to an arbitrary Grothendieck abelian category. Now, what about bounded categories? The special case of the bounded derived category of coherent sheaves was proved by Luntz and Olof if X is quasi-projective, and by Canonacco and Stellari if X has the resolution property. And as I said, Antio's paper is a real jump. He proved that that for any abelian category A, no hypothesis at all, the bounded below, and bounded above derived categories have unique enhancements. So somehow what we can do, which isn't in Antio's paper, is we can prove that the unbounded derived category has a unique enhancement unconditional. So for any A. So, as I said, okay, so I should say that our collaboration started by trying to see, we were fairly modest. We were just wondering whether the appeal to infinity categories was indispensable. In other words, can one prove Antio's much better results without appealing to infinity categories? We weren't trying to improve on his results. We were trying to understand whether the infinity category machinery was necessary. And in the end, we found completely different proofs which proved better theorems. Anyway, so I should say a tiny bit about the proofs. Okay, it'll have to be a tiny bit. So what is the key new idea? So we begin by looking at this map. The map from the homotopy category with whatever boundedness conditions to the derived category. And then we, inside both categories, we consider the full subcategories of complexes with zero differentials. So in other words, B of A and V of A have the same objects. The objects are the complexes whose, okay, going back to this diagram. K of A and D of A have the same objects. It's the morphisms which change. I remind you, the way you get the derived category is you take the homotopy category, the category where the objects are cochain complexes and homotopy equivalence classes of chain maps, and invert all the quasi-isomorphisms. This is the way you form derived categories, always. So the objects in these two categories at the bottom are the same, and B of A and V of A will just restrict the objects, and the restriction is that we just take the objects where the cochain complexes have zero differentials. There's nothing to stop me from considering the full subcategory of these objects. I mean, I'm going to formally write such a cochain complex as the direct sum of the shifts of the AIs. I mean, after all, the AIs are all the information. There are no differentials. The differentials are all zero. Now, in the category V, we have that the direct sum actually satisfies the universal property of the coproduct and the universal property of the product. But this is not true in the category D of A. In the category D of A, it needs proof that, I mean, it's not at all obvious, but that it satisfies any, but it turns out that if you take the half-infinite terms, they do satisfy either the product or the coproduct property. So this is a lemma which needs proof. But the key lemma, and the lemma which actually somehow the whole proof hinges on, is that K of A is generated by the category V of A in 3 steps. So if I have time, I'll go back to the proof. So this, yes, this really is the key lemma. And now I will explain how to pass from the key lemmas to the result. So suppose we have a DG enhancement of the derived category of A with some boundedness hypothesis, question mark. And we take C tilde to be the canonical enhancement of the homotopy category. We would like to enhance the Verdier quotient map pi to a DG functor from C hat to C, And the reason is that this would have to factor, I mean, C is defined to be C hat modulo the acyclics. And it's a theorem of Drinfeld's that given any dg functor from C hat, C tilde to if let me say it like this. If you have a dg functor C hat to C, such that H naught of pi tilde is a Verdier quotient map, then this functor has to agree with the canonical one. So the Verdier quotient map has a canonical description as a dg functor, and all others must be quasi-equivalent to it. So in other words, just by Drinfeld's theorem, this map is going to have to be a quasi-equivalence, but this, the first term, is a category, a dg category, which is independent of C. So if we do this, we will prove that C is quasi-equivalent to a dg category. As a dg category, C is quasi-equivalent to a dg category independent of C. So we would prove the uniqueness of enhancement. So how are we going to do this? So here's where we use lemma 1 or lemma 2. So we take V to be the inverse image of, in the dg category, of the objects with zero differentials, and let B and C be the inverse image of again the complexes with zero differentials. And our second lemma says that in 3 steps, the V generates all of K, which says that in 3 steps, B has to generate all of D. And this gives us that the category of perfect, the perfect closure of V has to be C tilde, and the perfect closure of B has to be C. So it suffices to produce a quasi-functor from V to B, since this would induce a quasi-functor from perf V to perf B. So we have to produce a quasi-functor from V to B. And okay, so now I'm going to simplify. Remember, in the category V, the direct sum is both the coproducts and the product. So in the category B, this isn't quite true, but if we pretend it's true, then in both categories, you could write hom from an object in V to an object in V as a giant product, and the map from hom V to hom B is just a T-structure truncation. And a T-structure truncation is something that you can do. I mean, a T-structure truncation is very natural. So you can define it in whatever context you want, for example, in C of K. So then the problem, then there's the technicality. As I said, the products and co-products in the derived category aren't, So in the derived category, it's not true. This isomorphism is true in V, but not in B. So in B, you have to be more careful. So in order to make a true argument of this, you do finite sums and let n go to infinity. And this becomes technical because letting n goes to infinity is difficult in derived categories. But okay, so this is the long and technical part of the paper, but it can be done. Okay, so this is a sketch of the main ideas of the proof. Now, the second major theorem in the paper by Canonacco, myself, and Stellari is that if X is a quasi-compact and quasi-separated scheme, then the category of sheaves of OX modules with quasi-coherent cohomology and the category of perfect complexes both have unique enhancements. So, what was known before? So, okay, so if X is separated, then the category of sheaves of OX modules with quasi-coherent cohomology is the same as the derived category of sheaves of OX modules with quasi-coherent cohomology is the same as the derived category of quasi-coherent sheaves on X. And so we are reduced to the previous case. If X, so in other words, the statement about dQc of X was known for separated X. The statement about perfect complexes was known relatively narrowly. So Luntz and Olof proved it when X is projective. Canonacco and Stellari improved it to X Noetherian and satisfying the resolution property. And Antio was, as I said, Antio was much more general. So he proved it as long as X is quasi-compact, quasi-separated. So the same generality in which our result works, but with the extra technical condition that it has to be zero completion. Let me not explain it because this extra technical condition turns out to be superfluous. So, so now what is, okay, let me not explain this remark. So what is the key idea of the proof? So the key idea of the proof is to reduce to the separated case. So you write X as a union of open affine subsets. I mean, X is quasi-compact and quasi-separated. The fact that it's quasi-compact means that it can be written as a union of finitely many open subsets. And the fact that it's quasi-separated means that the intersection of any of these, of any finite number of these open subsets is going to be quasi-compact. So it's going to be a quasi-compact separated scheme. I mean, it's a subset of an affine, so it's separated. So in other words, in the check cover of X by the UIs, all of the covering, all of the open subsets are separated. So you can apply the first theorem. You're in the simple case. So these categories all have unique enhancements by the separated case. And so now the idea is that any DG enhancement of the category of the relevant category of sheaves on X gives a Vernier quotient map to the relative an enhancement, to a canonical enhancement, which depends on C, of the relevant category of sheaves on the open subset. On the open subset, these are all unique by the uniqueness theorem that we proved for separated schemes. And C is the homotopy limit of these unique enhancements. So somehow the problem becomes to show that the uniqueness proof is compatible with taking homotopy limits. So this is a technical point, but it can be done. So anyway, so that's the heart of the proof. And then there are two more theorems. Okay. So those were both conjectures in Antio's papers, which we were able to prove. So the first says that if you take a Grothendieck-Abelian category, then the left completed derived category has a unique enhancement, and the unseparated derived category has a unique enhancement. So I'm not sure. It might actually be good, just as well to stop here, because I don't really want to. Okay, let me say epsilon more. I mean, I don't really want to define the terms. I mean, everything that's come up to now was very standard, but I don't know, left completion and unseparated might not be quite so standard. So the left completion, okay, the left completion is a left completion. It's left completion in the sense of Lurie, and I don't want to say anything about it. The unseparated derived category is somehow the generalization of the category of incoherent sheaves. It's the thing that's developed extensively in the papers of Drinfeld and Gatesbury. So instead of the derived category, you can look at a different category. You can think of both as somehow completions of the bounded derived category of coherent sheaves, different completions. Anyway, so as I said, Antio conjectured that both of these should have unique enhancements, and the conjecture turns out to be true in this generality. And I should probably thank you. Thank you very much.
Thank you. Thank you very much for the talk. Thank you. Okay, so I'll wait for questions. Any questions? Okay, so if there are no questions, I'll ask you. So this lemma that you had when you said that the homotopy category is generated by that VA in 3 steps.
Yes, okay, so yeah, thank you. I didn't even explain the terminology. I saw that I was running short of time, so I should first of all explain what the lemma means. Okay, so what does it mean to say that a category is generated by a subcategory in 3 steps? So this follows a definition of Bondal and Vandenberg. So if you take any triangulated category and any set of objects S, you declare S1 to be the set of all direct summands of all finite direct sums of shifts of objects in S. In other words, you take the objects of S, you allow yourself to shift them as much as you want, form finite direct sums as freely as you want, and form direct summands. So this is S1. And now you inductively define Sn by the formula that Sn plus 1 contains all extensions of objects in S1 by objects in Sn, and all their direct summands. So an object belongs to S2, an object y belongs to Sn plus 1 if there is a y dashed, so that y plus y dashed is an extension of an object in S1 by an object in Sn. Okay? So in other words, okay, I don't know how you count, but you obtain the objects in Sn by using no more than either n or n plus 1 extensions. Okay, so now I say, so with this, lemma 2 says that the objects of, so all cochain complexes in A are obtainable from cochain complexes with 0 differential in no more than 3 extensions. So this might seem surprising. So how do I do this? Well, I take any cochain complex. So I let Ki be the kernel of the map from Ai to Ai plus 1. Then the map, so it's just a definition. The map from Ai minus 1 to Ai must factor through Ki. So I have this factorization. And I consider all the maps from Ai minus 1 to Ki. So this is a map of complexes with 0 differentials. And if I form the mapping cone, it's the direct sum of things like this in appropriate degree. Okay, so far so good. And now I consider 2 maps. So this is the complex, this is the complex I call C star. C star is the direct sum of these. Now I have a map from Ki to C star. So its components are the identity map from Ki to Ki, and the map from Ki to Ai to Ki plus 1. And now I form the mapping cone on this map. And the mapping cone is A. So this is the piece of magic. The mapping cone is A plus a whole lot of trivial complexes, contractible complexes. So this needs checking, but it's true. So I've just built up any complex, the given complex, in 3 steps from complexes with zero differential. So, I mean, you could wonder where this comes from. So it follows from old ideas. So it follows by combining the ideas of these 4 papers. But okay, let me.
Right. Yeah, that was shocking. Thank you. Any other questions? Okay, so if there are no other questions, I'll thank you again for the great talk. Thank you. Okay, and I'll do the right thing and stop recording now.